Imagine a world where you can bring virtually any object you desire into reality, layer by layer, from a mere digital blueprint. That's the wonder of 3D printing, also known as additive manufacturing. It's a process that defies traditional manufacturing methods where material is added, not subtracted. From personalized chocolate bars to entire houses, 3D printing offers limitless possibilities.
Interestingly, the cost of acquiring 3D printers has been decreasing with the advancement of technology. Today, you can have your own 3D printer at home for just a few thousand pesos, making your creative dreams more accessible than ever. The commercial world, particularly industries like automotive and aerospace engineering, has enthusiastically embraced 3D printing. They've harnessed its power to produce spare parts, ushering in a new era of efficiency. Some forward thinkers even equate this transformation to a second industrial revolution. In the realm of medicine, 3D printing is akin to medical fairy godmother, already making waves in bionics, prosthetics, and digital dentistry. While many of these innovations are still in their early stages, the potential they hold is nothing short of astonishing. The future of medicine is poised for a revolutionary transformation thanks to the creative possibilities offered by 3D printing. It's an exciting journey of discovery that's reshaping healthcare as we know it. But that's just the tip of the iceberg. Before we get into how it works today, let's go back in time a bit to see how 3D printing evolved to as we know it.
Now, let's embark on a journey back to the 1980s, a pivotal era when 3D printing was in its infancy, taking its first steps into the world. Buckle up as we take a quick trip down memory lane, exploring the highlights of this remarkable period. In 1981, Hideo Kodama introduced the concept of rapid prototype using photopolymers. Think of it as the birth of creating 3D models out of thin air. Then, in 1984, Charles Hall stepped into the scene with stereolithography. Picture this. He could turn liquid polymers into solid objects using a magical ingredient called ultraviolet light. Fast forward to 1986, Charles Hall founded 3D Systems, and the first 3D printer, the legendary SLA-1, made its debut in 1988. The year 1989 was a double whammy. Joe Beeman and Carl Deckard introduced selective laser sintering, a technique that fused powder materials using lasers. Meanwhile, Scott Crumb co-founded Stratasys and introduced fused deposition modeling. In 1990s brought more excitement. In 1992, DTM released its SLS 3D printer, pushing the technology even further. By 1999, the medical world had embraced 3D printing with a groundbreaking moment, printing a urinary bladder. Then in 2005, Dr. Adrian Bower gave us the RepRap open source concept, opening doors for self-replicating 3D printers. And let us not forget the Spectrum Z510 3D printer, which could not only print in color but in HD too. In 2008, the Darwin RepRap 3D printer came to life, a printer that could self-replicate. It was like the 3D printing world saying, "Hey, we are open for business, and you can join the fun too." Now, let's talk about the evolution of 3D printing. It's mind-blowing. Number 1, accessibility. 3D printing went from being an exclusive club for the elite to becoming accessible for everyday people. Now you can have a 3D printer right in your living room. It's like magic for the masses. Number 2, medical advancement. The impact on medical field has been extraordinary. 3D printing has given us the power to create custom medical implants, prosthetics, and even complex organs like urinary bladder. It's revolutionizing healthcare. Number 3, diverse materials. In the early days, it's all about plastics. But now, 3D printing can handle an array of materials, including metals. Ever thought of printing a gold or silver ring? Now it's possible. Number 4, versatile applications. 3D printing has become a swift army knife in the world of technology, whether it's a crafty unmanned aircraft or bring an intricate designs to life. It's a versatile marvel. This historical journey has shown us how 3D printing evolved. But how does this incredible technology actually work? Stay tuned as we delve into the mechanics and processes behind 3D printing, unveiling the secrets that bring your wildest creation to life.
Now, let's take a deep dive into how 3D printing works. Here's a general overview of the process. Number 1. Design. The first step in 3D printing is creating a 3D model of the object you want to print. This model is typically designed using computer-aided design or CAD software. It defines the shape, size, and structure of the object. Number 2. Slicing. The 3D model is then sliced into thin horizontal cross-sections using slicing software like CAM. This software generates a set of instructions known as G-code. This guides the 3D printer on how to build each layer. Number 3, we've got the printing itself. The 3D printer reads the G-code and begins the printing process. The specific 3D printing technology used will determine how each layer is created. I will discuss 7 later. Now, number 4, we've got the post-processing. After the object is 3D printed, post-processing steps may be necessary, such as cleaning, sanding, painting, or assembly. Now, there are different types of 3D printing technologies, each suited to different applications and materials. Number 1, we've got Fused Deposition Modeling, or FDM. This is the most common consumer 3D printing technology, known for its affordability and simplicity. It is a popular material extrusion method where the thermoplastic filament is heated and extruded through a nozzle. It's like a hot glue gun creating layers of material. FDM is popular for creating prototypes, hobbyist projects, creating functional parts, or even household items. Next, we've got stereolithography, or SLA. SLA provides high-resolution, smooth, and detailed prints, making it suitable for creating intricate parts and models. Uses a vat of liquid photopolymer resin and a UV laser to solidify each layer. It's akin to sculpting with light. SLA is used for producing detailed, high-resolution parts in industries like dentistry, jewelry, and aerospace. Next, we have selective laser sintering, or SLS. It is often used for producing functional, high-precise, and high-accurate parts, especially in the aerospace and automotive industries. In SLS, a laser fuses powdered material layer by layer. It's similar to laser welding in a controlled environment. Next, we have binder jetting. Ideal for large-scale productions, it can print various materials including metals, ceramics, and polymers. It's cost-effective and fast. This method combines powdered material with a liquid binding agent to create layers. It's popular for producing large and complex parts such as architectural models and sand molds for metal casting. Next, we have directed energy deposition. It offers precision in adding material with exceptional control. It's employed in aerospace, high-tech industries, tooling, and oil and gas sectors to repair or add material to existing parts. Next, we have sheet lamination, LOM, and UAM. Both methods are cost-effective and excel in creating complex geometrical parts with finesse. Sheets of material are bonded together to form each layer. It's like a 3D collage of materials. Last but not the least, we have vat photopolymerization, SLA, and DLP. These methods provide high-quality surface finishes and are suitable for creating premium products with fine details. They are known for high surface quality and detail, making them suitable for producing dental models, figurines, and detailed prototypes.
3D printing materials include wire filaments like ABS, PLA, PVA, and TPE, each with distinct characteristics. Powder materials such as wood filament offer unique aesthetics, but it can be abrasive. Printable waxes find use in specialized applications like jewelry casting, while liquid resins are versatile and utilized in SLA and DLP 3D printing processes. Now, there is a big role with hardware and software in this dynamic technology. The interaction between hardware and software is critical for 3D printing. G-code commands are sent from a computer to the printer, with firmware interpreting and executing them to ensure precise printing. And now that we've established how 3D printing works, let's explore how this interaction translates into real-life implementation and examples.
The technology of 3D printing is constantly evolving and is being implemented in many sectors of our society. Here are some of the most notable implementations of 3D printing. Medical technology. 3D printing is used in the medical field through prosthetics. Bioprinting is cheaper and faster to make than previous traditional methods of creating prosthetics. Furthermore, it also prevents the use of animal testing. The most common usages for bioprinting are for limbs such as hands, legs, and arms. But some emerging technologies include 3D printed organs such as kidneys, eyeballs, hearts, blood vessels, and many more. The printing of prosthetics is not limited to humans but even for animals. Companies such as 3D Pets make prosthetics for dogs, cats, pigs, ducks, and many other animals. For the space industry, nowadays, scientists use 3D printing for components in rocket engines. By using materials that can withstand high temperatures, scientists utilize 3D printing for more efficient and cheaper components. Some of the components of the Perseverance rover created by NASA to explore signs of prehistoric life on Mars were even 3D printed. 3D printing is being utilized in so many industries nowadays. One of the most surprising and notable is the sports industry. Currently, Wilson is creating a 3D printed airless basketball made with elastomeric polymer. Wilson hopes for their prototype to be the future of balls used in various sports someday. We can see now how 3D printing is being used in so many industries. Time can only tell how much of our products will be made through 3D printing. Even food being 3D printed is something that scientists are working on now. One thing is for sure, 3D printing technology is here to stay and will continue to evolve to greater implementation.